Hello there, and welcome to the Sleepy Science Channel. Tonight, we drift gently into the magnificent realm of solar systems, where worlds stranger than imagination move in a cosmic dance of time, gravity, and light. Our own solar system is just one story among billions, a single chapter in an endless celestial library filled with suns, moons, rings, and mysteries. Out there, beyond the faint echo of our own star, the universe holds twin suns that rise and set together, molten worlds circling too close to their fires, and even orphan planets wandering freely in the darkness. This journey is more than a voyage through space. It is a voyage through wonder itself, a calm exploration into the hidden architecture of the cosmos. What we find will not only surprise us but redefine what we think is possible. Some discoveries challenge our understanding of life, others challenge our definition of a planet, and all of them remind us how vast and flexible nature truly is. As you listen, breathe slowly, let the night settle around you, and feel your thoughts grow lighter, as though floating among the stars themselves. Some solar systems host planets that orbit two suns at once. Imagine sunsets that arrive in pairs, tides pulled in duet, and skies glowing with alternating hues as stellar companions pass behind and before each other. In these circumlunar systems, a planet must weave a path through constantly shifting gravity, tracing an orbit that looks less like a circle and more like a braided ribbon of light. Yet even here, in this apparent chaos, stability can emerge. Gravity may be complex, but it often finds repeating rhythms when distances and masses fall into balance. From a planet's surface, the brightness of the sky would wax and wane as the two stars drift closer or apart, painting seasons utterly unlike those of Earth. Studies of their formation show that dust and ice can still gather into planets, even amid the turbulent push and pull of two suns. Growth may pause and resume, spiral waves may pass through, but nature is patient. Wherever physics allows a pocket of order, matter finds a way to settle, condense, and build. These worlds are proof of cosmic flexibility, of creation thriving even in complexity, expanding our sense of what climates, atmospheres, and perhaps even life itself might look like. In other systems, planets move in reverse, orbiting their stars backward, defying intuition. These retrograde orbits are like cosmic rewinds, as if the universe itself pressed a reverse button. They arise when a young planet is tilted by a passing neighbor, twisted by a slanted disk of dust, or knocked during the chaotic adolescence of star systems. The result is a world whose orbital plane tilts sharply away from its star's equator, sometimes just a little, sometimes completely reversed. Such geometry reshapes weather and tides, because day and year pull in opposing directions. The effect can twist winds, stretch seasons, and carve out alien cycles of light and dark. But these backward orbits also record history. They are celestial scars that tell of ancient collisions, distant passers-by, and gravitational battles long ended. By studying the tilt and direction of these worlds, astronomers can reconstruct dramas billions of years old, stories of cosmic turbulence hidden in otherwise tranquil skies. Each retrograde planet is like a file in a detective's cabinet, a piece of evidence proving that the universe's script is never neat, that even stars and planets have untidy pasts. And still, amid this diversity, patterns emerge. 1 in every 5 sun-like stars may have a planet roughly the size of Earth. Through patient surveys, astronomers watch for tiny dips in starlight, the gentle shadows cast when planets pass in front of their suns. When the data are corrected for angle and sensitivity, a striking truth appears: small worlds are everywhere. Many orbit within temperate zones where liquid water could persist, given the right atmosphere. These worlds may not all have oceans or breathable air, but their abundance changes everything. The search for life is no longer about rare jewels. It has become a systematic catalog of possibilities, a careful map of nearby shores. Each time we measure a transit or trace a star's wobble, a new candidate steps forward. With future telescopes, we will sift the light of their skies for hints of clouds, winds, and chemistry, perhaps even the whisper of life. The implication is humbling: the night is not empty. It is full of potential, dotted with countless little harbors where time and physics have woven stories we have yet to read. Some planets, however, have no star at all. cast adrift by gravitational encounters or born alone, these rogue planets roam the interstellar dark without a sun to anchor them. Their nights are eternal. Their skies hold no sunrise, only the faint glow of distant galaxies. Yet even in such solitude, they may not be dead. Some retain thick insulating atmospheres that trap internal heat. Others hide oceans beneath crusts of ice, warmed by radioactive decay or the lingering heat from their formation. Occasionally, a wandering world may pass close enough to another star to stir its tides and awaken temporary warmth, a fleeting echo of daylight before continuing its endless drift. Detecting such loners is difficult, for they cast no transit shadow. But sometimes we catch them by their faint infrared glow or by the brief brightening they cause when crossing a distant starlight beam. Their existence proves that planetary birth and eviction are both common outcomes of crowded youth, and that the galaxy is sprinkled with cold, drifting islands of stone and ice, a hidden archipelago between the shining lamps of the stars. Some solar systems we've found are unimaginably old, almost as old as the universe itself. These ancient stars formed when the galaxy was young, their matter enriched by only a few generations of supernovas. Around such primitive suns, astronomers have detected the fingerprints of planets. Their chemistry is lean, lacking in heavy elements like iron or silicon, yet somehow, dust still clumped, and worlds still formed. These systems have orbited quietly for billions upon billions of years, surviving galactic mergers, gravitational tides, and waves of newborn stars bursting into light. Their planets, if they still breathe thin air, have endured epochs beyond any human sense of time, weathering every possible variation of climate. They are cosmic fossils, time capsules preserving the earliest recipes for world building. Studying them links the dawn of the cosmos to the planetary diversity we see now, proving that the creation of worlds began soon after the first stars ignited and has continued ever since, humming through eternity. Planets also wander within their systems, migrating from the cradles where they formed. In their youth, surrounded by swirling gas and dust, they trade momentum with their environment, slowly spiraling inward or outward. Some drift gently, others are thrown violently, their paths redrawn by gravity's invisible hand. When the gas disperses, the dance continues as planets tug one another, exchanging energy, stretching or shrinking orbits, even swapping places entirely. This grand rearrangement can send an icy giant into a warm realm or park a massive planet close to its star, reshaping climates across the system. Migration sculpts resonances, clears belts of debris, and triggers cascades of comets that may deliver water and organic molecules to inner worlds. It explains why so many systems defy the neat pattern. Planetary systems are living architectures, molded by friction and gravity, their final arrangements whispering of past encounters long forgotten. Some solar systems are more crowded than ours, filled with multiple planets packed tightly within the orbit of Mercury. Each circles its star in mere days or weeks, yet somehow remains stable. Their harmony is delicate, like pearls strung on intertwined threads, each bead's pull balancing the next. From the surface of one world, nearby planets would appear enormous in the sky, swelling from crescents to glowing disks over the course of a week. In these close quarters, tides rise high, atmospheres churn, and celestial rhythms beat with hypnotic precision. Crowding does not mean chaos, it means efficiency. When conditions are right, nature prefers to build many medium worlds rather than a few giants, distributing material in snug orbits that hum like a perfectly tuned instrument. Their diversity, rocky, gaseous, hazy, bright, shows that even planets born side by side can evolve into vastly different characters. A single sun can host a family of experiments, each world offering a different answer to the question of how matter and light shape climate, geology, and time. Yet not all systems are so generous. Some form with no rocky planets at all. If a star's protoplanetary disk lacks heavy elements, or if gas giants form early and greedily absorb the available material, then the inner regions may never build solid ground. Instead, such systems become collections of Neptunes and Jupiters, their cores small, their atmospheres vast and puffy under the heat of their stars. Farther out, the cold preserves rings and moons sculpted from ice. In these places, the concept of habitable surface disappears entirely, There is only wind, gas, and shadow. And yet even here, the artistry of nature is clear. Every variation tells us more about how the universe experiments with its own rules. Some systems may have only debris belts and comets. Others, silent brown dwarfs barely bright enough to call suns. Together, they form a cosmic mosaic of possibilities, each arrangement a unique balance of gravity, temperature, and time. Across the galaxy, solar systems are not exceptions but expressions, diverse outcomes of the same universal ingredients mixed in infinite combinations. From twin suns to rogue wanderers, from backward spinning planets to ancient survivors, each system is a laboratory of cosmic design, testing what it means to be a world. As we map their orbits, analyze their atmospheres, and listen to their faint signals, we realize how deeply connected we are to this grand experiment. Our own solar system, with its balance of warmth and distance, is just one harmonious chord in a vast galactic symphony. Every discovery adds another note to the music, another ripple in the rhythm of creation. So as you close your eyes tonight, imagine drifting outward, past the calm edge of Earth's gravity, past the orbit of Neptune, into the silent sea where countless suns shimmer like floating lanterns. Each light you see is a story, each story a family of worlds. Somewhere, two suns rise together. Somewhere, a lonely planet sails without a dawn. Somewhere, a world circles backward, tracing the scars of its youth. And somewhere, perhaps not far from here, another small blue marble waits quietly beneath the glow of its star, breathing, turning, dreaming. The night sky above us is not just a view, it is a map of possibilities, a reminder that creation never truly rests. There are solar systems that defy everything we once thought necessary for a world to exist. There are no continents to drift across molten mantles, no volcanoes to recycle crust, and no shorelines to cradle oceans, yet chemistry still thrives. In clouds, in the upper haze of gas giants, and on the frozen faces of distant moons. Magnetic fields born from swirling interiors can shield dense atmospheres from the violent tempests of their parent stars, preserving layers where molecules react and evolve. These rockless families remind us that planet formation is not obliged to reproduce Earth's familiar blueprint. The universe is not limited by our expectations. It experiments endlessly, crafting ensembles where air and ice are the main players while stone takes a hidden, supporting role. Some solar systems operate in perfect harmony, their planets locked together in resonant chains, moving in clockwork precision where for every fixed number of orbits one planet completes, its neighbor finishes another exact count. This synchronized motion, carved from migration through the early disk, prevents chaos and ensures that paths never cross. The planets become like dancers keeping to a shared rhythm, their gravitational pulls weaving a balance that can endure for billions of years. From afar, the pattern leaves faint signatures in the timing of their transits, and the tiny tugs they exert on each other, allowing astronomers to weigh them and probe their hidden structures. For any potential inhabitants, the sky would hold predictable spectacles, bright companions that return in regular intervals, gliding across the heavens like notes in a repeating cosmic melody. These harmonic systems prove that gravity, when tempered by time and gentle friction, can compose its own stable music from the raw noise of dust and gas. It is not a rigid perfection but a living resilience, a natural cadence that records the history of each planet's migration written into the rhythm of their years. Elsewhere, entire systems of planets have formed where every world is nearly the same size, as though stamped from a cosmic mold. In our solar system, scale varies wildly, from tiny Mercury to the immense bulk of Jupiter, but in these distant families, uniformity reigns. The planets, often somewhere between the size of Earth and Neptune, line up in compact orbits, creating rows of super-Earths or mini-Neptunes, each distinct in atmosphere and surface, yet eerily similar in scale. Their differences arise not from mass, but from position, from the chemistry of their birthplaces, and from collisions or migrations that reshaped them long ago. Such uniformity hints at conditions that distributed material evenly across the disk or gravitational checks that kept competition balanced. These systems challenge our sense of normalcy. They suggest that the universe may prefer symmetry over extremes, harmony over hierarchy. And perhaps, in their evenness, such systems might offer greater long-term stability for life, worlds sharing gravity rather than dominating it. Some planets, however, live on the very edge of endurance, skimming so close to their stars that metals vaporize in their skies. These worlds race around their suns in mere days or hours, with temperatures soaring high enough to melt iron and silicates. On their day sides, nothing solid can last. Rocks sublimate directly into atmosphere, creating metallic vapors that the fierce winds carry to the dark side. There, the gas cools, condensing into glittering clouds that may rain droplets of molten metal back onto the surface. It is weather beyond comprehension, a cycle of vaporized mountains and metallic storms, a shimmering testament to nature's persistence in the face of extremes. These ultra-hot worlds show us that planet formation does not avoid the furnace, it adapts to it. They endure where we once believed nothing could exist, revealing the astonishing versatility of matter and the artistry of survival under radiation intense enough to unmake stone. Not every planet is so blessed as to keep its atmosphere. Some are stripped bare by the constant assault of stellar winds and radiation. Close-orbiting rocky worlds are especially vulnerable, their gases torn away particle by particle until nothing remains but naked rock. On these scorched bodies, the star-facing side can reach temperatures that bake even metals, while the night side plunges into deep freeze, a realm of frozen darkness just a few thousand kilometers away. With no air to scatter light or carry sound, the silence is total, the surface unprotected from meteoroids or cosmic rays. And yet this exposure turns such planets into pristine historical records, preserving the scars of impact and erosion exactly as they form. By studying these airless worlds, astronomers learn how atmospheres evolve and vanish, how magnetic fields can mean the difference between protection and desolation, and how fragile the balance of pressure and temperature. Even in their silence, they tell stories about endurance, loss, and the thin line between a living sky and empty space. Some planets begin far from their stars and only later wander inward. A planet's birthplace, it turns out, is rarely its permanent home. In the cold outskirts of young systems, dust and ice stick easily, building large, heavy cores. These distant embryos, buffeted by currents of gas, may slowly spiral inward like rafts caught in a cosmic tide. Sometimes the cause is drag within the gaseous disk. Sometimes it's the gravitational push and pull of other forming worlds. A giant planet born in frozen darkness can thus migrate inward and settle close to its star, becoming a hot Jupiter, a massive gas world that could never have formed in its current position. This migration reshapes the entire system, scattering smaller planets, disturbing belts of asteroids and comets, and sometimes locking survivors into new orbital rhythms. Each inward traveler leaves a fingerprint, a trace of motion written into the final structure of its home. By mapping these traces, astronomers can reconstruct the long migrations that turned chaotic disks of dust into orderly systems. Planetary placement, we now know, is only a snapshot in time, not a birth certificate but a moment in an ongoing dance that lasts for eons. Even the grandest systems are not eternal. When massive stars reach the end of their lives, they can explode as supernovas, brilliant deaths that outshine entire galaxies for a few brief weeks. In that blinding instant, shockwaves race outward, tearing apart nearby planets, vaporizing atmospheres, and scattering debris into interstellar space. Those worlds that are not obliterated outright may still be sterilized by the blast, their chemistry erased by radiation more intense than a million suns. Yet from this destruction comes creation. The heavy elements forged in these dying stars, iron, gold, carbon, oxygen, are hurled across the galaxy, seeding new clouds of gas where new stars and planets will one day form. A single supernova can both end and begin entire solar systems. The fragments that survive, shattered moons, molten cores, orphan rocks, drift through the void, the ashes of one system destined to become the soil of another. The story of solar systems, therefore, is cyclical: creation, evolution, and destruction, each phase writing new possibilities into the galactic fabric. Even familiar features like rings can reach impossible scales elsewhere in the cosmos. Saturn's graceful bands are beautiful, but in some systems, exoplanets have ring structures so vast that their total diameter would dwarf a small star. These colossal disks may be the remnants of shattered moons, captured comets, or debris that never quite formed a companion. When such a planet passes in front of its star, the rings begin to block light long before the planet itself arrives, and continue long after it has passed, creating unusual patterns of dimming that first revealed their existence. Maintaining such massive rings is no easy feat. Gravity should cause them to clump or disperse, yet they persist, suggesting dynamic histories, recent collisions, tidal breakups, or complex balances between heat, radiation, and rotation. Within these majestic halos, moons may form over time, sweeping clean paths and growing into full-fledged companions. These outsized rings remind us that even well-known planetary features can exist on scales far beyond imagination, their shimmering spans turning the concept of planetary ornament into cosmic architecture. And beyond the rings, some systems contain moons larger than Earth itself. These are not mere satellites but true worlds in their own right, orbiting gas giants like miniature planets around miniature suns. Such exomoons could harbor atmospheres thick enough to breathe, oceans of liquid water, or complex geology driven by the ceaseless tug of tides from both their planet and their star. Their days and nights are woven from multiple cycles, a dance between planetary rotation and orbital motion that creates intricate rhythms of light and shadow. Detecting them is a monumental challenge, as their signals are faint and often lost in the glare of their hosts, but tiny fluctuations in timing and brightness hint that some may already have been glimpsed. If confirmed, these colossal moons will expand our concept of habitability beyond planets to include the worlds that circle them, proving that life might thrive not only under a sun, but beneath the reflected glow of a giant neighbor. And so, as we piece together the stories of these countless systems, a grander pattern emerges. The universe is not content with uniformity. It builds rocky worlds and airless husks, hot Jupiters and frozen exiles, systems that hum in harmony and others that tumble toward destruction. Some worlds are smooth and silent, others blaze with storms of molten metal or winds of diamond dust. Yet, in every variation, one truth endures: where physics allows it, nature will find a way to create. The cosmos is a restless artist, sculpting with gravity and time, layering experiment upon experiment until every possibility is tested. Solar systems are its sketches, temporary yet eternal, fragile yet vast. They are laboratories of stability and chaos, each one a unique expression of balance, chance, and endurance. Our own solar system, with its delicate spacing and familiar order, is only one composition among billions. Somewhere out there, a world rains iron instead of water, a moon larger than Earth circles a ring giant, and a system destroyed by supernova dusts the birth of new stars far away. All of it, every orbit, every collision, every beam of light, belongs to the same cosmic symphony that began when the first stars lit the darkness. As we gaze upward, we are not just looking into distance, but into time, into generations of worlds endlessly rising, falling, and being reborn. There are moons in the cosmos that could cradle life as kindly as Earth itself. A moon with Earth-like mass and water could thrive under the protective magnetosphere of its parent planet, bathed in the light of both its star and its planet's reflection. Such a moon might orbit a giant world, warmed not just by sunlight but also by the gentle pull of tidal forces, stirring its oceans and maintaining a stable climate. The discovery of such a place would redefine where we look for life and expand our imagination of what home means beyond Earth. Yet, the universe also holds countless planets utterly alone, worlds that move through space without a single moon to accompany them. These solitary planets may have lost their moons through violent collisions, or perhaps they were born in quiet, barren regions of the protoplanetary disk where no satellite could ever take shape. Without a moon stabilizing tug, their axial tilt could wobble wildly, leading to chaotic seasons and unpredictable climates. The absence of tides would still the rhythmic breathing of their seas, leaving coastlines largely unshaped by lunar influence. Their nights would be profoundly dark, unsoftened by a silver companion in the sky. Yet, such loneliness carries scientific beauty. These moonless worlds offer a pristine environment to study the internal mechanics of planets unaltered by tidal forces. Even emptiness, in the language of the cosmos, tells a story about formation, scarcity, and the quiet aftermath of creation. Some worlds have moons that are older than the planets they orbit, a strange reversal of cosmic order. In these rare systems, a moon might have formed independently in the swirling protoplanetary disk, existing long before its eventual planet assembled. Later, gravity captured this ancient wanderer, transforming it from a drifting relic into a bound companion. These preplanetary moons hold the chemical memory of earlier epochs, different isotopes, crater histories, and mineral patterns that reveal conditions the host planet never experienced. Their surfaces might record impacts and radiation from a time when the system was still a maelstrom of dust and gas. This blurring of roles between planet and moon challenges the neat hierarchies we imagine for solar systems, showing that cosmic architecture often depends on timing, chance, and gravitational choreography. Each mismatched pair deepens our understanding of how celestial bodies exchange roles and how formation overlaps across vast spans of space and time. The first exoplanets ever discovered did not orbit a shining young sun, but a corpse, a pulsar, the spinning remnant of a dead star. After a massive supernova explosion, what remained was a dense neutron star emitting beams of radio waves like a cosmic lighthouse. Astronomers noticed tiny, precise deviations in these pulses, caused by the gravitational pull of orbiting planets. These worlds survived, or perhaps reformed, amid the radiation-filled ruins of a stellar death. They existed where logic once said life and planets could not, circling a beacon of destruction. The discovery was astonishing. It proved that planetary formation can occur even after catastrophe, that nature rebuilds worlds from chaos itself. Those first pulsar planets opened the door to the field of exoplanetary science, teaching humanity that the universe is far more inventive and resilient than our expectations. Every planet found since, every hot Jupiter, icy Neptune, or super-Earth, traces its scientific ancestry back to that discovery around a dead sun. In other solar systems, planets race around their stars faster than Earth spins once on its axis. Some complete an orbit in mere hours, shorter than a single Earth day. These ultra-short period planets cling perilously close to their stars, locked in orbits where gravity and radiation wage constant war. The heat on their daysides can soar to thousands of degrees, vaporizing rock and metal into shimmering atmospheres that might glow with silicate vapor and metallic mist. Their nightsides, shielded from the star's glare, could be frigid and airless. Tidal forces stretch and compress these planets continuously, generating internal friction that melts rock and drives volcanic activity. To stand on such a world, if one could survive it, would mean seeing the star dominate half the sky, while the horizon shimmered with blazing gases. Though tidally locked, these worlds test the boundaries of orbital endurance, proving that planets can exist in places that seem impossibly hostile, balanced on the razor's edge between destruction and stability. Far from such infernos, some planets are made almost entirely of water. These water worlds defy the terrestrial model we know. They are vast global oceans without continents, their surfaces endlessly rolling under thick, humid skies. Beneath their waves, immense pressures may create exotic ices like Ice 7 or Ice X, phases of water unknown on Earth, where molecules lock into geometric cages. Above, vaporous atmospheres shimmer with reflected starlight, giving the planet a bluish halo when viewed from afar. Winds sweep across oceans that stretch thousands of kilometers without a single island to break them. In such a world, volcanoes might erupt beneath crushing depths, and life, if it exists, would evolve with no awareness of land, trees, or sky, only the boundless, eternal sea. The existence of these planets expands the meaning of habitability, suggesting that oceans alone may cradle life in countless alien forms. Then there are the diamond planets, cosmic treasures forged in unimaginable heat and pressure. Around carbon-rich stars, planets can form with so much carbon that their mantles crystallize into pure diamond. Beneath a thin crust, layers of sparkling solid carbon might extend for thousands of kilometers, capped by molten seas of carbon or methane. These worlds are heavy and beautiful, shimmering like jewels against the blackness of space. Their surfaces could be dark and mirror smooth, while their interiors glitter with incomprehensible wealth. On such planets, the idea of treasure becomes meaningless. Diamond is as common as dust. These worlds remind us that geology itself transforms under different elemental recipes, that the familiar becomes alien when forged in the crucible of other stars. Some planets orbit their stars so tightly that a full year lasts only a few hours. They complete revolutions so fast that the idea of morning and evening becomes meaningless. In the span of a human meal, a sunrise and sunset might both occur. On their daysides, rocks evaporate, forming glowing metal-rich atmospheres that trail behind like comet tails. Rain on such planets could fall as molten iron, while silicate clouds drift in scorching winds. The radiation is so intense that it continually strips away their atmospheres, reshaping the planet over cosmic time. Locked in eternal rotation, one hemisphere burns endlessly under stellar fire while the other freezes in perpetual night. These planets are laboratories of extremes, where physics is tested to its limit and survival becomes an act of defiance against nature's fiercest forces. And then there are the giants so bloated they could float on water, planets as light as cork. Among the thousands of exoplanets discovered, a few stand out for their astonishingly low densities. Though as large as Jupiter or even bigger, their mass is spread so thin that they would be buoyant in an earthly ocean. These puffy planets are made mostly of hydrogen and helium, their atmospheres swollen by heat from their stars or residual warmth from formation. Seen in silhouette during transits, they dim their stars only slightly, yet their presence ripples across the light curve like a ghostly breath. Their fragility challenges models of how gas giants form and survive. They show that even the largest worlds can be delicate, balloons of starlit-era drift in the cosmic wind. Across this vast spectrum of possibilities, water worlds, diamond worlds, pulsar orbits, and moonless plains, the universe displays its restless creativity. Planets are not built to a single pattern, nor confined by the rules our own solar system suggests. Some are burned bare, others drowned in endless seas, some are as heavy as lead, others lighter than foam. The boundaries of habitability, beauty, and endurance stretch far beyond Earth's narrow range. Every discovery reshapes our sense of belonging in the cosmos, teaching that life, stability, and wonder can emerge in the most unexpected places. Whether orbiting the embers of a dead star or racing around a living one in hours, each world adds a verse to the universe's endless poem, a song of matter, motion, and memory written across the infinite dark. They are known as super puffs or cotton candy planets, vast gaseous worlds that orbit dangerously close to their stars, where the intense stellar heat inflates their atmospheres to colossal proportions, making them appear as if they were made of vapor and light. Despite their immense size, their actual mass may be only a few times that of Earth, rendering them delicate and vulnerable to even the slightest cosmic disturbance. A marginal increase in stellar radiation or a close encounter with another planet or star could strip away their fragile envelopes entirely, leaving behind nothing but a barren core. These mysterious worlds challenge our understanding of planetary formation, suggesting that they either grew rapidly around massive frozen cores before drifting inward, or gathered their gases slowly and gently in regions of calm before being pulled closer to their stars. Their very existence represents the universe's remarkable precision, a balance so fine that even a minor shift in temperature, pressure, or radiation could spell their end. Yet they survive, shimmering examples of cosmic fragility that reveal how adaptable and diverse planetary systems can be. Beyond these airy giants lie the true heavyweights of the cosmos, super Jupiters. Our Jupiter may be the undisputed titan of our solar system, but elsewhere, there exist planets 10 or even 20 times its mass, massive enough to dominate entire star systems with their gravity yet not quite large enough to ignite nuclear fusion and become stars themselves. These immense gas giants sculpt their surroundings with invisible hands, pulling neighboring planets into new paths, stirring belts of debris, and sometimes preventing smaller worlds from forming at all. Their atmospheres are crushingly dense, layered with exotic chemicals forged under pressure and heat so immense that they defy laboratory imitation. Some orbit perilously close to their suns, glowing faintly in the infrared like living embers, while others drift far from warmth, where their cloud tops freeze into alien crystals colder than anything on Earth. The sheer scale of these giants stretches the very definition of what it means to be a planet, reminding us that even within familiar categories, nature creates unimaginable variety. But the universe doesn't stop there. Some worlds orbit not one, but 2 or even 3 suns, tracing elegant paths through the gravitational ballet of multiple stars. While Earth follows a single, steady sun, these circumbinary or multimodal planets circle entire systems that twist, wobble, and pulse as they move. The skies of such planets would be magnificent, 2 or 3 sunrises and sunsets each day, their hues shifting as the stars dance across the heavens. Seasons there would not follow simple patterns, for warmth and cold would depend not only on distance from a single sun, but on the ever-changing relationships between several blazing companions. To survive such chaos requires balance almost beyond comprehension, yet these planets do, their orbits stable over billions of years, their gravity synchronizing with that of the stars in perfect celestial choreography. They are proof that stability and chaos are not opposites, but partners in the cosmic dance, giving birth to harmony in the most turbulent corners of creation. Still, not all planetary systems exist in quiet isolation. Some are born within dazzling star clusters, dense cosmic neighborhoods where thousands of stars ignite together, so closely packed that a night sky would never grow dark. On such a planet, the heavens would blaze with perpetual starlight, every horizon glowing with suns. For a long time, astronomers doubted whether planets could survive such violent beginnings. Passing stars might rip them from their orbits, or drown them in radiation. Yet we have found worlds nestled peacefully amid these stellar metropolises, orbiting serenely despite the cosmic traffic. Occasionally, a nearby star passes too close, slightly altering their orbit or climate, yet many persist freeans, bearing witness to the resilience of planetary formation. The fact that such worlds exist proves that creation is both robust and flexible, able to persist even in regions of fierce radiation and gravitational chaos. Standing on one of these planets would be like living beneath the ceiling of eternal day, surrounded by the relentless brilliance of newborn suns, each one a reminder that beauty can flourish even in crowded, dangerous places. But these systems are not safe forever. The galaxy itself is a restless ocean, and stars drift through it like ships on uncharted seas. Occasionally, their paths cross, and when that happens, the result can be cataclysmic. A close encounter between 2 stars can tug planets from their orbits, fling comets inward to bombard inner worlds, or eject entire systems into interstellar space. Some planets may find themselves exiled, cast adrift as rogue wanderers with no sun to warm them, doomed to eternal night. Though such encounters are rare on human timescales, they are inevitable across the lifetimes of stars. The traces of ancient disruptions may linger in oddly tilted or elongated orbits, scars left by forgotten cosmic collisions. Even our own solar system might bear such silent fingerprints, evidence that our peaceful arrangement is the product of immense luck. These encounters remind us that no solar system is truly alone. All are travelers in a galaxy alive with motion, chance, and transformation. Yet, from destruction often comes rebirth. When a star like our Sun reaches the end of its life, it sheds its outer layers in a shimmering wave of gas, leaving behind a white dwarf, a quiet ember of its former brilliance. Around some of these stellar corpses, astronomers have discovered swirling disks of debris, the shattered remains of earlier planets and moons. And within these ashes, new worlds can form. The dust and gas that once belonged to ancient planets gather once again, recycling cosmic material into new creations. These second-generation planets may contain elements forged in the cores of their dead stars, heavy metals, rare isotopes, and exotic compounds that make their geology utterly unique. Though they orbit faint, dying stars, some may retain enough heat deep within their crusts to sustain hidden oceans or molten interiors. The existence of such worlds blurs the line between death and rebirth in the universe, showing that endings are often just the beginning of something new. Sometimes, entire solar systems arise from the collisions of titanic clouds of gas drifting through the galaxy. When 2 of these immense nebulae meet, their impact compresses hydrogen and dust into dense pockets that collapse under gravity, giving birth to stars and planets. The violence of their origins leaves lasting marks. Planets with tilted orbits, chaotic spacing, or unusual compositions, each a fingerprint of the turbulence that forged them. Some worlds may grow massive before the storm calms, others form from leftover fragments long after the chaos fades. Often, multiple stars are born from the same collision, traveling together through space as siblings, each with its own planetary family. This grand cosmic interplay, collisions, compression, collapse, shows that creation is not always peaceful. Sometimes, the universe builds its most beautiful systems through the fire and force of cataclysm. Yet not every system completes its creation. Some stars are surrounded by disks of dust and gas that never fully coalesce into planets. These glowing clouds, suspended for billions of years, reflect their stars' light in haunting halos of silver and gold, ghostly reminders of worlds that might have been. In some cases, the disk simply lacks enough material to form planets. In others, turbulence or interference from nearby stars prevents solid bodies from taking shape. Sometimes, unseen planets within the disk subtly sculpt the dust into rings and lanes, maintaining a fragile balance without ever clearing the path completely. These half-formed systems are like frozen snapshots of creation, offering astronomers a glimpse into the delicate process that builds worlds. The dust they shed drifts back into the galaxy, seeding future generations of stars and planets, a cosmic cycle that never truly ends. Far from the warmth of suns, on the outer edges of solar systems, lie planets so distant that their stars appear no brighter than a pinprick in the eternal night. These remote worlds are locked in cold isolation, their surfaces buried beneath layers of ice thicker than mountains, their atmospheres frozen solid into crystalline shells. Yet, even in this frozen silence, life persists in the form of energy. Radioactive decay and residual heat from their formation can create hidden oceans beneath the ice, where warmth lingers in defiance of the dark. Their orbits are vast and slow, taking thousands or even tens of thousands of Earth years to circle their distant suns, giving them seasons that last longer than all of human history combined. Time moves differently there, glacial, immense, and eternal. These far-flung planets remind us that the architecture of solar systems extends far beyond what we can easily imagine, reaching into realms where sunlight no longer rules. In these frozen frontiers, life and chemistry bend to new laws, and the universe continues its endless experiment with form, energy, and endurance. Across all these cosmic possibilities, from super-puffs and super-Jupiters to reborn worlds, binary systems, and frozen exiles, one truth emerges: there is no single way to be a planet. The universe builds its creations from chaos and order alike, balancing destruction with renewal, silence with motion. Each solar system tells a different story, written in the language of gravity, light, and time. And in their endless diversity, we find reflection, that even in the vast cold emptiness of space, balance, beauty, and survival are never accidents, but the natural rhythm of existence itself. We have discovered planets that orbit their stars on steeply tilted axes, defying the orderly patterns once assumed to be the norm of the cosmos. While most planets, like those in our solar system, circle their stars in planes aligned with the stellar equator, some follow erratic paths tilted wildly above or below this imaginary line. These misaligned orbits tell stories of ancient turmoil, collisions between planets, close gravitational encounters with passing stars, or perhaps distortions in the early protoplanetary disk that seeded them. If such a world were home to life, its inhabitants would witness seasons of bewildering irregularity. The sun might rise far in the northern skies for decades, only to drift slowly toward the south across centuries, plunging climates into cycles beyond anything Earth has known. Deserts could turn to tundra, frozen plains could bloom and vanish again. These tilted worlds preserve the fossil memory of celestial violence, each orbit an echo of the chaos that once shaped its destiny. Other planets, too, break the mold, following not circular but highly elongated paths, eccentric orbits that carry them alternately close to their star's inferno and far into icy night. For such a world, a single year could contain cataclysms. When near its star, temperatures might soar to thousands of degrees, boiling seas and spawning colossal storms. Then, as it swings outward, those same vapors could freeze into glaciers. The entire surface would pulse with vast climatic transformations over the course of a single orbit. These elliptical wanderers are shaped by gravitational quarrels, planetary shoves, stellar flybys, or lingering turbulence from their violent births. They reveal that not all solar systems are serene clockworks. Some beat to rhythms sculpted by instability and chance. The result is a breathtaking variety of worlds, each molded by gravity's invisible, unpredictable hand. But gravity does not only shape, it also destroys. When a planet drifts too close to its star, the intense tidal forces can tear it apart atom by atom. Its crust cracks, its atmosphere peels away, and streams of vaporized rock spiral outward like ribbons of fire, forming glowing trails that astronomers can sometimes see across the darkness. Over millions of years, a solid planet may unravel completely, leaving only a molten core and a cloud of debris that eventually becomes a shimmering ring or dust belt. These doomed planets remind us that the same gravitational force that births worlds also consumes them. Gravity creates and uncreates in endless cycles, a quiet cosmic sculptor whose work is both magnificent and merciless. In other solar systems, vast asteroid belts take the place of planets, stretching across millions of miles and containing mountains, boulders, and glittering dust. Some belts are hundreds of times larger than the one between Mars and Jupiter in our own system, their countless fragments the ruins of planets that never formed or the wreckage of those destroyed by ancient collisions. The skies of a planet near such a belt would shimmer with constant light, streaks of burning meteors and reflections from uncountable stones. These belts are not merely remnants, they are archives of creation. Within their frozen compositions lie the original ingredients of planetary birth: carbon, water, metals, and organic molecules. Over time, these fragments can rain down on inner planets, delivering the raw materials for oceans and life. In this way, even destruction serves purpose. From the shards of failed worlds come the seeds of living ones. Sometimes, solar systems host not just one habitable zone, the region where liquid water can exist, but several. A binary star system, for example, may create multiple overlapping bands of warmth and stability, each capable of nurturing life in its own way. In one zone, rocky planets may bloom with oceans and forests. Farther out, giant gas planets could shelter moons with hidden seas beneath ice. These multiple habitable zones broaden our idea of where life might arise, suggesting that the cosmos may teem with possibilities beyond the narrow band Earth occupies. As stars evolve, these zones drift and transform. A planet once too cold may thaw into habitability, while another once temperate may slowly boil. Each world enjoys its golden age for a cosmic heartbeat before change sweeps it away. The shifting nature of these life-bearing regions reveals that habitability itself is not a fixed gift, but a fleeting alignment of time, distance, and heat. Stars, too, change dramatically over their lifetimes, dragging their solar systems into new realities. As a star burns through its hydrogen, it grows hotter and brighter, pushing the habitable zone outward. Worlds that once thrived are scorched, while frozen exoplanets may suddenly awaken, their ice melting into oceans that glimmer for a geological instant before refreezing. These transformations mean that the story of life in the universe is one of constant adaptation, a rhythm of birth, death, and rebirth as stars and planets evolve together. Our own Earth is not immune. Billions of years from now, our sun's gradual brightening will boil away the oceans, leaving only barren continents under a swollen sky. Yet, in that same future, some distant world may just be entering its perfect age of life. New solar systems often arise in the luminous clouds of nebulae, vast nurseries of gas and dust where starlight and gravity weave creation together. Within these glowing veils, gravity draws threads of hydrogen and helium into knots that ignite as new stars. Around them, disks of dust swirl, coalescing into planets, moons, and asteroids. The radiation from nearby massive stars sculpts and scars these forming systems, stripping away atmospheres, melting ice, and sparking exotic chemistry. A planet born in such a place would see skies ablaze with color, crimson nebular clouds, electric blue light from newborn stars, and shadows of dust like drifting mountains in the heavens. The materials in these regions are ancient, atoms forged in supernovae, metals birthed in the deaths of older stars, and so every new planet carries within it the memory of the cosmos. In the glow of nebulae, creation and destruction meet, and the universe writes its next chapter from the ashes of the last. Astonishingly, planets can begin forming even before their stars are fully born. In the earliest stages, before a protostar ignites into steady fusion, its growing gravity shapes a disk of swirling matter. Within that disk, grains of dust stick together, forming pebbles and then boulders, the building blocks of planets. Long before the first starlight shines, the architecture of an entire solar system is already being traced in the dark by invisible hands. As the star gathers mass and flickers into life, these planetesimals carve lanes through the dust, clearing paths that will later become orbits. The temperature, chemistry, and turbulence of this early disk decide whether the system will host rocky Earth-like planets, icy giants, or barren belts of rubble. By the time the star's core ignites and stabilizes, its planetary family may already be taking shape, orbiting in silence beneath the newborn light. Not all systems, however, reach such harmony. Some are paragons of order, their planets gliding neatly in circular orbits along the same plane, perfectly aligned with the gentle rotation of their star. Others are monuments to chaos, wild tapestries of misaligned paths, looping orbits, and planets moving backward against the star's spin. These differences reflect each system's unique history. Some formed peacefully, others were ravaged by collisions, turbulence, or gravitational disruptions. Each solar system is a record of cosmic memory, written not in words but in motion. In studying both the orderly and the chaotic, astronomers discover that beauty is not limited to symmetry. There is elegance, too, in the unpredictable, in the tilted, in the broken dance of the stars. And then there are the unfinished worlds, planets that never got their chance to be born. In the furnace of a young star's awakening, the intense radiation can sweep away the remaining gas of a protoplanetary disk before its clumps of matter fully coalesce. What remains are half-formed fragments, massive asteroids, rubble piles, or moon-sized bodies too small to become true planets. They drift for eternity, scarred by collisions that no longer heal, relics of a race they almost won. Some may one day collide and merge into new planets, others will crumble into dust, feeding future generations of stars. Their frozen silence whispers of lost potential, reminding us that creation is as much about what never happens as what does. All these worlds, tilted and eccentric, shattered and serene, half-born and reborn, reveal a universe endlessly inventive. From chaos it finds rhythm, from destruction, renewal. Planets are not mere objects but stories, each orbit a narrative of struggle, chance, and endurance. Whether aligned in perfect harmony or flung into erratic dance, each world bears witness to the timeless truth that the cosmos is alive with motion, a grand, ongoing act of creation, where even the smallest fragment of dust carries within it the memory of stars and the promise of worlds yet to come. Even the most promising beginnings in the universe can be cut short when a young star matures too fast, turning fierce before its planets have a chance to form. Astronomers have detected solar systems being born around baby stars, protostars that glow faintly as they collect mass and evolve toward the main sequence. Around these infant suns swirl luminous disks of dust and gas, warmed by the gentle radiance of their growing cores. Within these glowing rings, the first signs of planet formation appear, distinctive gaps, circular lanes, and clumps of material that mark the gathering of new worlds. These are not yet the cool, serene planets we imagine, but molten spheres wrapped in thick atmospheres of nebular gases and hot ice, their surfaces in constant motion. Every part of these systems speaks of creation, dust spiraling inward, gas giants carving luminous paths through fog, and chemical reactions birthing the early ingredients of weather, oceans, and sky. Watching these young systems through powerful telescopes is like seeing a time-lapse of our own solar system's childhood, each snapshot revealing how the familiar might once have looked in its chaotic infancy. Every recorded image captures a fragment of that cosmic youth we can never relive, a reminder that even the stars had beginnings as fragile as ours. Yet just as stars and planets are born, they also die. Some solar systems show clear signs of planetary destruction, where astronomers have found evidence that worlds once thrived but no longer exist. Around certain stars, glowing rings of metallic dust or clouds of vaporized rock orbit in patterns too unnatural to be accidental. White dwarfs, The dense remnants of dead stars sometimes reveal polluted atmospheres filled with silicon and iron, proof that they have devoured their own planets. These fragments are all that remain of systems torn apart by tidal forces, obliterated during stellar expansion, or shattered by colossal collisions. Even moons and pebbles continue to orbit in silence, tracing the ghostly outlines of what was once a living planetary family. Planetary destruction reminds us that solar systems are temporary arrangements, fragile and fleeting. Their lifespans include not only birth and evolution but also decay and erasure. Yet even in destruction, there is renewal. The debris left behind, dust, metal, gas, can one day collapse again into new stars and planets, recycling the same atoms into the next generation of cosmic life. In the dense heart of galaxies, where stars cluster tightly together, solar systems can form under entirely different conditions. The galactic core is far from empty. It teems with stars, dust, gas, and immense gravitational forces. Here, stars are born in a storm of radiation and gravity. They're forming disks bombarded by energy from nearby supernovas and jostled by passing suns. These harsh conditions produce planets rich in heavy elements, forged quickly from material recycled by older stars. Worlds formed in such environments may have compressed cores or dense, metallic atmospheres, their orbits constantly perturbed by gravitational tides. If life ever arises in such crowded places, it would grow beneath skies crowded with thousands of suns, brighter and busier than any view from Earth. The galactic core reminds us that planetary creation is not limited to peaceful suburbs like our own solar neighborhood. It happens everywhere, even amid chaos and noise. Some planets orbit stars so hot that their atmospheres are made entirely of vaporized metal. On these ultra-hot exoplanets, temperatures soar high enough to melt iron, sodium, and magnesium, turning them into gases that shimmer like liquid mirrors. Their skies blaze with metallic clouds, refracting light into brilliant colors that telescopes can detect across light years. Winds on such worlds can reach thousands of kilometers per hour, carrying metal vapor from the blazing day side to the frozen night, where it cools into glittering clouds or rains molten droplets. Lightning storms crackle through metallic haze, painting the heavens with electric fury. There is no oxygen or nitrogen here, only fire and metal forged into atmosphere. These planets redefine what we imagine possible, showing that nature's creativity knows no bounds. What seems impossible on Earth may be ordinary elsewhere. On some other planets, storms rain glass or even gemstones. In these exotic worlds, atmospheres rich in silicates and minerals condense into crystals instead of water droplets. High-speed winds fling molten rock into the upper atmosphere, where it cools into microscopic shards of sapphire, ruby, or glass before falling like shimmering rain. Gravity drags these crystals down through violent storms, scouring the surface or bouncing across molten oceans of metal. These weather systems turn the sky into a forge and the land into an anvil, where beauty and destruction coexist. Every storm becomes a spectacle, a glittering rain of jewels across alien horizons, reminding us that even the harshest environments can produce breathtaking wonder. Many of these discoveries stretch the definition of what a planet can be, proving that beauty and danger are constant companions in the cosmos. Some worlds live forever divided between light and shadow, tidally locked planets that always face the same side toward their star. On such planets, the day's side is scorched by unending sunlight, while the night's side lies in perpetual darkness and ice. Between them runs a narrow twilight band where winds swirl endlessly, balancing heat and cold in fragile equilibrium. Oceans, if they exist, would cling to this terminator zone, either frozen solid nor boiled away, offering a possible refuge for life. The idea of habitability must be reimagined here, a world half dead and half alive, where the sun never rises or sets, and existence depends on surviving in the eternal dusk. Recent models show that such planets could host stable climates, their atmospheres redistributing heat efficiently enough to sustain life. In these strange dual worlds, life would adapt not to day and night, but to the permanent geometry of light itself. Some planets spin so rapidly they nearly tear themselves apart. Their rotation stretches them into oblate spheroids, bulging at the equator, their atmospheres whipped into hurricane-force winds. A day on such a planet might last only a few hours, and the centrifugal forces at the equator nearly overcome gravity's pull. These spinning worlds glow with storms and shock fronts, their skies alive with magnetic auroras and blazing streaks of plasma. They are young, energetic, and unstable, remnants of violent cosmic collisions or rapid migrations that left them spinning like tops on the edge of destruction. They are monuments to the extremes of physics, where motion itself becomes a form of art. Other planets dazzle in an entirely different way, reflecting light so intensely that they shine like cosmic mirrors. These brilliant worlds may owe their luster to cloud decks filled with crystals, to vaporized minerals that condense into reflective hazes, or to glassy surfaces forged by relentless heat. As storms sweep across their surfaces, their brightness flickers and shifts, revealing wind speeds and atmospheric layers to distant astronomers. Some of these mirror worlds orbit so close to their stars that their skies are constantly remade, minerals boil, ride the winds, and fall again as glittering frost. Others are cooler, cloaked in ice or salt that keeps them luminous even in dim light. Each one acts as a signal flare across the galaxy, telling us what its air is made of through subtle changes in reflected starlight. Yet for all the shining worlds we can see, there are also those we cannot, planets that wander alone in the dark, unbound to any star. These rogue planets drift through the galaxy like cosmic orphans, ejected from their systems during violent early encounters or formed in isolation where no star ever took hold. Without a sun, their surfaces are shrouded in perpetual night, lit only by the faint red warmth of their own internal heat. Their skies hold no sunrise or sunset, only endless blackness. Yet even these lonely travelers may not be lifeless. Some might carry thick atmospheres that trap heat, or subsurface oceans warmed by radioactive decay. These worlds are reminders that even in the deepest darkness, the universe finds ways to persist. Each of these strange, fascinating planets, from the molten to the icy, the mirror bright to the starless, adds another verse to the story of creation. Together, they show us that the cosmos is not uniform or predictable, but a wild canvas painted in extremes, where metal can become air, where jewels fall as rain, where life might thrive in twilight, and where even in ruin, the seeds of new worlds are sown. Where pressure grows immense and relentless, buried oceans may endure beneath shells of frozen gases, kept liquid by the gentle but persistent murmur of radioactive warmth from the rock below. These hidden seas lie within planets so faint they're nearly invisible to even the keenest eyes, yet they betray their presence through momentary gravitational lensing events, when their mass bends distant starlight for a fleeting instant before vanishing again into the cosmic dark. A few of these worlds glow faintly in infrared light, like embers drifting across a vast black sea, soft reminders that the process of planet-making is anything but neat, and that our galaxy is sprinkled with countless lonely wanderers carrying the remnants of their origins across space. While most known planets are composed of familiar mixtures of rock, ice, and gas, theory permits stranger worlds, bodies born under exotic conditions where chemistry and pressure twist matter into rare and unfamiliar states. In such places, carbon might crystallize into colossal planetary diamonds, or hydrogen might compress into metallic seas that conduct electricity like oceans of fluid metal. Some hypothetical worlds may even hold ultradense forms of matter that pack astonishing mass into compact sizes, creating planets so heavy and gravitationally intense that meteoroids vanish into their surfaces without leaving a trace. These dense worlds might have formed in regions enriched by the ashes of ancient supernovas or near compact stellar remnants where immense tidal forces and pressures push matter to extremes unseen in our own solar system. Though no probe has yet visited such a place, their gravitational fingerprints, seen in the trembling of nearby stars, suggest that nature's creativity in shaping planets stretches far beyond the small sampling we have observed close to home. Astronomers have even caught stars devouring their own planets, a grim but natural outcome of stellar aging. As a star swells into a red giant, its outer layers can expand enough to touch the orbit of a nearby planet. The doomed world's gas begins to spiral inward, leaving behind subtle chemical fingerprints, surges of lithium, iron, and other elements that don't appear through normal stellar fusion. Some of these gluttonous stars also spin faster than expected for their age, their rotation rejuvenated by the angular momentum of their planetary meal. Around white dwarfs, the dim, dense remnants left behind after sun-like stars die, the evidence is just as striking. Heavy elements appear in their atmospheres even though gravity should have pulled them inward long ago. The only explanation is a steady drizzle of planetary debris, asteroids, moons, or shattered planets, falling in from disrupted orbits. Infrared glows from hot dust rings and irregular dips in starlight complete the scene, revealing a cosmic menu of endings where gravity reclaims what it once allowed to roam freely. Every such system tells a story of formation, decay, and renewal, showing that even destruction contributes to the galactic cycle of worlds. Some planets wield magnetic power beyond imagination, their fields dwarfing Jupiter's already mighty magnetosphere. Within these giants, deep metallic or saline oceans churn under tremendous pressure, while rapid rotation drives a dynamo effect that converts internal heat and motion into planetary-scale magnetic storms. The result is a fortress of magnetism, fields so vast they sculpt bow shocks in the stellar wind and spin out tails millions of kilometers long. Near the poles, auroras flare so intense they can outshine their host star in radio wavelengths. These dazzling displays tell us much about what lies beneath: a metallic hydrogen core, a molten ocean, or a complex blend of materials forged under impossible weight. When such magnetized worlds orbit close to their stars, the interplay between magnetic and stellar forces can even heat their upper atmospheres, alter their chemistry, and create unique auroral colors unseen elsewhere. By listening to the faint radio murmur of these worlds and watching for ultraviolet flashes, astronomers can weigh their hidden hearts and glimpse the unseen engines that drive their cosmic weather. Beyond the planets themselves, entire solar systems reveal intricate patterns of formation and memory. Many stars are surrounded not by a single asteroid belt like ours, but by multiple concentric rings of leftover building blocks, each one a silent archive of a system's history. Warm inner belts teem with rocky debris, while colder outer zones harbor frozen ices and complex organic molecules. The gaps between them are not random voids. They are footprints of invisible planets, bodies that have swept lanes clean or trapped dust into rhythmic resonances through gravity's quiet dance. Collisions within these belts grind larger fragments into fine dust, which glows in infrared light and sketches the unseen architecture like chalk outlines against a dark blackboard. In young systems, these collisions happen frequently, causing the dust brightness to flicker and fade over mere human timescales. In older systems, the belts endure as fossil records, traces of once crowded orbits that tell of how worlds were born, destroyed, and rearranged across eons. Not all stars hosting these systems are grand or easily visible. Many are tiny red dwarfs, stars so cool and dim that they appear as mere crimson embers in the vastness of space. Yet they are the most common type of star in the galaxy, and their planetary systems may be among the most plentiful. Around these quiet fires, small planets huddle close, receiving just enough warmth to sustain temperate climates despite the faint light. Because the disks of material around red dwarfs last much longer than those around brighter suns, small worlds have more time to form and stabilize. To human eyes, the daylight on such a planet would be a deep, ruddy glow, its parent star looming large and steady in the sky. Though young red dwarfs often erupt with flares, over time they settle into long-lived calm, allowing atmospheres, especially those with magnetic shielding, to endure for billions of years. These systems are thus prime candidates for habitability, representing a vast hidden reserve of potentially life-bearing worlds scattered through the Milky Way. Because their orbits are short, their transits repeat frequently, letting astronomers study their atmospheres, climate rhythms, and even the passing of alien seasons. Indeed, the possibilities circling these small stars are anything but small. In still other cases, planets orbit so close to their stars that they live within the flow of the stellar wind itself. Every active star releases a continuous stream of charged particles, a solar wind, that rushes outward in all directions. Some planets sit within this breath, their skies perpetually stormed by high-energy plasma. At the boundary where the wind meets a planet's magnetic field, immense shock fronts form, accelerating particles that cascade toward the poles and ignite auroras spanning entire hemispheres. For worlds without strong magnetic defenses, this wind can strip away their atmospheres, sculpting long plasma tails and heating their skies from within through induced electric currents. These environments are brutal, yet deeply revealing. By studying how a planet's air responds to these cosmic tempests, scientists can infer the planet's density, magnetic structure, and chemical composition. Even the rhythm of its auroras can mirror the heartbeat of its parent star, a luminous thread connecting sun and world in a shared cosmic pulse. Some planets endure such fierce stellar heat that they begin to lose themselves to space. These worlds grow comet-like tails, not of ice, but of their own evaporating atmospheres. Hydrogen streams away in ghostly ribbons, and heavier vapors, released from molten rock, trail behind like smoke from a slow-burning ember. The planet's orbit shapes these tails into graceful curves, while the push of starlight fans them outward across millions of kilometers. When one of these evaporating planets crosses in front of its star, the tail begins dimming the starlight before the planet itself arrives and continues long after it departs, creating a prolonged, asymmetric transit. Different wavelengths of light reveal the tail's composition: hydrogen here, sodium there, perhaps traces of vaporized silicates, each component changing over time as stellar winds wax and wane. Some tails fragment into clumps or dissolve entirely, only to reform as the planet completes another orbit, an eternal cycle of loss and renewal. These delicate structures, invisible to the naked eye, become luminous signatures of survival under impossible heat, telling us that even in the most hostile corners of the galaxy, worlds continue to evolve, adapt, and express the endless creativity of cosmic physics. Taken together, these discoveries paint a portrait of a universe both diverse and dynamic. From diamond worlds buried in darkness to molten exoplanets shedding tails of vapor, from magnetic titans glowing in radio light to dusty rings that whisper the history of creation, every system speaks of balance. Between order and chaos, creation and decay, warmth and cold, gravity and escape. The more we look outward, the more we learn that planets are not rare jewels but the very grains of structure in the galaxy's fabric. Each one carries a story shaped by pressure, chemistry, time, and chance, a story that, in its own alien way, mirrors the restless heart of the cosmos itself. There are living records scattered across the cosmos that show how fragile worlds lose their breath to their suns, revealing the pace at which a planet's atmosphere can thin, evaporate, and vanish into the void. These records, written in gases escaping from planetary skies, tell the story of endurance and loss, how starlight itself becomes both giver and taker of life. Yet, even as some worlds fade, others persist in unimaginable places. Astronomers have found planets that orbit black holes, the darkest objects in existence, where not light but gravity reigns supreme. Around these collapsed stars, daylight might come not from a sun but from a faint companion star, or perhaps from a glowing accretion disk of gas swirling furiously toward the black hole's event horizon. These planetary orbits must be precisely balanced, wide enough to avoid being torn apart by tidal forces, yet close enough to remain bound against the gravitational tugs of passing stars. Because such worlds are nearly impossible to see, the evidence comes in fragments, subtle gravitational lensing events that reveal a compact mass with a lighter companion, or flickers in the light of an accretion disk that betray a planet shepherding gas into gentle waves. The physics of such systems is harsh, but not entirely hostile. If the radiation is moderate and the environment stable, moons, oceans, and even atmospheres could survive for millions of years, orbiting in the calm geometry of spacetime's deepest wells, where the ruler of all things is gravity itself. Not every planet, however, experiences the luxury of night and day. Some worlds live in eternal daylight, tidally locked to their stars so that one hemisphere faces perpetual blazing light, while the other lies buried in endless shadow. On the day side, the sun never moves. It hangs fixed in the sky, blazing unceasingly, burning continents into deserts and boiling oceans into vapor. Towering clouds of steam or mineral dust rise endlessly, carried by vast convection currents between searing light and frozen dark. The terminator, the twilight band between these extremes, may be the only refuge where heat and cold find an uneasy balance, allowing winds, clouds, or perhaps even life to persist. To exist on such a world is to know no dawn or dusk, only the eternal rhythm of contrast, the unbroken glare of day, and the absolute stillness of a night that never ends. These tidally locked planets remind us that the experience of time, light, and shadow, so central to life on Earth, is not a universal rule but a local privilege. Other worlds glow with their own light. Some are still so young or massive that they radiate residual heat from their violent births, their molten interiors shimmering with energy that escapes through glowing clouds and molten surfaces. Others are heated by tidal forces, pulled and squeezed by the gravity of nearby giants in endless cycles of compression and release. Their heat oozes outward, creating surfaces dotted with lava lakes, vaporizing metals, and atmospheres that shimmer with incandescent vapors. From afar, such worlds appear as faint, glowing orbs, miniature suns orbiting their parent stars, their radiance a temporary inheritance from creation itself. Over millions of years, they will cool, darken, and join the silent company of colder planets, but for now, they blaze as young fireballs of cosmic adolescence, reminders that planets are not merely passive stones but engines of energy and transformation. Even mature solar systems can retain the dust and chaos of their youth. Long after their planets have formed, many systems remain veiled in faint clouds of debris, microscopic grains, comet fragments, and shattered rocks still drifting between worlds. These dust clouds, glowing softly in infrared light, trace out the invisible architecture of the system, lanes sculpted by planets, arcs curved by gravitational tugs, and gaps cleared by hidden companions. In young systems, this dust is so thick it hides the stars themselves, turning them into glowing embers behind a warm fog. In older systems, it persists only as a faint haze, a lingering echo of early violence and ongoing collisions. Each grain of dust is a relic of impact and creation, of moons breaking apart or new ones forming, of comets colliding and asteroids grinding each other to powder. These swirling remnants tell us that no solar system is ever truly finished. Creation and destruction are constant companions in the choreography of orbiting worlds. Planets can even form in the shadows of giants. Around massive stars, behemoths that burn tens of thousands of times brighter than our Sun, conditions seem hostile to creation. Their intense radiation melts, strips, and blows away nearby material, leaving only a harsh glare and high-speed winds. Yet, in the quiet shadows cast by dense gas clouds or within eddies sheltered behind massive disks, small pockets of stability emerge. In these sanctuaries, silicate grains cling together, ice coats dust, and larger bodies begin to coalesce. Tiny seeds of planets born in defiance of their parent star's fury. When such a star eventually ends its brief but brilliant life in a supernova, its planets may face annihilation from the blast, yet some survive, their surfaces enriched by heavy elements forged in that final explosion. These survivors are extraordinary, worlds infused with rare metals and radioactive isotopes, carrying within them the very ashes of their creator. They are planets born from fire and death, literal children of the stars. Not all stars are kind to their planets. In some systems, radiation becomes a slow, relentless predator, stripping away atmospheres molecule by molecule. Ultraviolet light and charged particles bombard the upper layers of air, heating them until they escape into space like smoke rising from a dying ember. Over billions of years, once thick atmospheres vanish, leaving barren rocks exposed to the void. The lighter gases, hydrogen, helium, disappear first, followed by heavier molecules that fall back as strange metallic rains or cling briefly before being lost forever. Some planets shrink visibly as their mass erodes, their shapes altered by invisible storms of radiation and wind. In the most extreme cases, nothing remains but a rocky core or a faint ring of dust marking where a world once was. The remnants drift in silence, their substance dispersed into space, seeding the galaxy with traces of ancient air and lost oceans. Nothing in the universe endures unchanged, not even planets themselves. Sometimes, however, planets come not from the dust of their stars but from other corners of the galaxy. Astronomers have discovered interstellar visitors, objects born around distant suns but flung free by gravitational chaos, wandering the darkness for eons before being captured by a new system. When such a traveler falls under a star's influence, it becomes part of a new family, its orbit eccentric and tilted, its chemistry alien to its new home. These captured worlds are cosmic refugees, carrying the fingerprints of other galaxies and stellar generations within their cores. Their presence blurs the boundaries between systems, showing that space is not made of sealed islands, but of interconnected pathways where even planets can trade homes. Over time, some of these visitors settle into stable orbits, while others are eventually flung out again, continuing their lonely migration through the interstellar sea. Each one is a testament to the restless, dynamic nature of gravity's web, the quiet truth that no solar system owns its members forever. The process of creation itself is equally varied. In many systems, planets form slowly, gathering dust and gas over millions of years. But some systems take cosmic shortcuts. Instead of gradual accretion, immense gas giants may form almost instantaneously through gravitational collapse. When a region of a protostellar disk becomes too massive, it can fold in on itself, condensing into a giant planet in mere thousands of years, a blink of cosmic time. These rapid formations create enormous, turbulent worlds with chaotic interiors, their atmospheres layered with ingredients that never fully mixed. Such planets may migrate through their systems, disrupting orbits, scattering smaller worlds, and reshaping the entire structure of their neighborhood. They are the impulsive creations of the cosmos, born not through patience but through sudden collapse, demonstrating that nature's creativity knows both slow artistry and spontaneous genius. Solar systems themselves can even rise from the ashes of destruction. After a supernova, when a massive star explodes and scatters its material across light years, the debris can cool, condense, and form new stars surrounded by the enriched dust of the dead. From this matter, new planets emerge, built from the heavy elements synthesized in that stellar death. These worlds, born from remnants of past suns, contain the raw materials for life: carbon, iron, silicon, oxygen, all products of the nuclear furnaces that once burned in other skies. Thus, every new world is also an inheritance, a continuation of a story written by the stars that came before. Across the galaxy, this endless cycle continues, planets forming, glowing, eroding, and sometimes surviving in impossible places. Some circle black holes, their paths curving through the distorted fabric of space-time. Others bask eternally in daylight or drift through dusty nebulae where stars are still being born. Some are stripped bare by radiation, while others thrive in quiet orbits around dim red dwarfs. A few are refugees, cast out from one system and captured by another. Together they form an atlas of possibility, a living record of how gravity, chemistry, and time weave the universe into an ever-changing dance of creation and decay. Each world, no matter how strange or distant, adds one more verse to the grand story of existence, that nothing in the cosmos stands still, that every beginning is also an ending, and that even in silence, the universe remembers how to breathe. When a massive star dies in a supernova, it does not simply vanish, it gives birth to new beginnings through destruction. The explosion scatters the heavy elements it forged in its fiery heart, casting iron, gold, uranium, and other complex materials into the vastness of space. These elements, born only in such cataclysms, enrich nearby clouds of dust and gas, ensuring that when new stars and planets form from them, they are composed of more than just hydrogen and helium. They are infused with the very ingredients that make rocky worlds and life possible. In these enriched clouds, radioactive isotopes generate internal heat, and dense metallic cores take shape, forming planets with layers of complexity and chemistry far beyond those of primordial gas worlds. Our own solar system carries echoes of such an origin. Traces of supernova elements linger in Earth's rocks, silent testimony to our birth from the ashes of stellar death. Creation and destruction, it seems, are two sides of the same cosmic rhythm. Even in regions dominated by black holes, the most extreme environments in the universe, planets can form. Around stars that orbit these gravitational abysses, disks of gas and dust swirl into intricate spirals, compressed and stretched by invisible tides. Stability is rare but possible, allowing young worlds to emerge in the shadow of annihilation. The radiation from the black hole's accretion disk can alter their atmospheres, perhaps even shaping their chemistry in ways unknown. These planets live within gravitational maelstrom where both space and time are bent, yet the same universal laws of matter allow creation to persist amid chaos. Elsewhere, some planets orbit so close to their stars that their very matter cannot stay solid. The day sides of these worlds are seas of molten minerals. Iron flows like water, rocks vaporize into the air, and temperatures climb so high that even atoms begin to lose their electrons, turning atmospheres into blazing plasma. On these infernal planets, vaporized rock rises, cools, hardens into glass, and then melts again, an endless cycle of transformation where geology becomes weather and the crust itself is reborn every few days. They remind us that the concept of a solid planet is merely one possibility among many in the cosmos. Some worlds cannot even hold onto their skies. When a planet lacks magnetic protection or strays too close to its star, ultraviolet radiation tears at its atmosphere, stripping it molecule by molecule. Hydrogen and helium escape first, streaming into space like glowing tails of a comet, followed by heavier gases as the relentless wind continues its work. Over time, the planet is left bare, a core exposed to the void, the remnants of its atmosphere drifting through space as faint trails of gas. Atmospheres, we learn from these examples, are fragile things, temporary shelters in a universe where even the most complete skies can fade into nothingness. Not all planets are solid or small either, some are vast, ethereal giants made almost entirely of gas. These behemoths, composed of hydrogen, helium, and traces of methane or ammonia, have no surface to stand upon. Beneath their colorful cloud bands, the pressure grows so immense that gases compress into metallic hydrogen, a substance that behaves like a liquid metal, conducting electricity and generating immense magnetic fields. Their atmospheres are in perpetual motion, with storms that dwarf anything on Earth, winds that circle the planet in mere hours, and lightning flashes brighter than the sun's reflection on our oceans. Their very existence challenges our definitions of what a planet can be, worlds without surfaces, sculpted from nothing but air and motion. Yet the universe's creativity doesn't end there. Some solar systems are graced with multiple habitable planets, each bathed in the gentle warmth that allows water to remain liquid. Imagine a system where 2 or 3 Earth-sized worlds share the same sun, orbiting close enough to see one another as bright arcs in the sky. One may be covered in oceans, another rich in volcanic plains, and a third wrapped in soft clouds that drizzle over vast continents. If life emerges on one, the others might become targets for exploration or even interplanetary contact, their civilizations gazing at each other's glowing disks in wonder. These systems hint that companionship may not be rare in the cosmos. Life may find neighbors under the same star. Farther out in the cosmic cold, other planets exist in perpetual night. Orbiting their stars at enormous distances, they receive so little light that even their skies are dimmer than our moonlit nights. On these frozen worlds, air solidifies into frost, oceans freeze solid, and mountains are made not of stone but of ice. There is no warmth for life as we know it. Even tectonic activity halts as the planet's core cools. Yet, within the ice, strange chemistry might still occur. Trapped gases, ancient heat, and hidden oceans of ammonia whisper of possibilities beneath the silence. Beyond them are planets so dense they seem impossible by normal physics. Their masses suggest that they formed through colossal collisions, multiple young planets smashing together, their metallic cores fusing while outer layers were stripped away into space. Inside these dense worlds, pressure and heat give rise to materials unknown to Earth, metallic crystals and exotic alloys that bend light and magnetism in unpredictable ways. The gravity would be crushing, the air heavy, the very ground feeling as if it pulls at every step. Such planets are cosmic monuments to the violence of creation, reminders that even destruction can build something enduring. Not every solar system is rich with ice like ours. In some, conditions are too hot or turbulent for frozen materials to ever form. Without ice to trap water or other volatiles, these systems create barren, metallic worlds. Planets scorched and dry, their skies thin, their surfaces cracked and airless. There are no comets to deliver oceans, no glaciers to temper the climate. These places prove that water, so abundant to us, is not a guarantee in the universe, it is a privilege. And in the absence of ice, worlds evolve in alien ways, with chemistry and geology unlike anything seen on Earth. Yet even the dry systems are alive with motion. Some planets there experience weather beyond comprehension, storms the size of continents, winds faster than sound, and lightning storms that rage for centuries. On such worlds, the energy of heat and rotation combine to form patterns of chaos that never repeat, painting the skies in colors no human eye has ever seen. The diversity of these systems, molten, frozen, gaseous, or metallic, shows that the universe does not repeat itself. Each solar system is a new experiment in physics and time, a unique story of matter under pressure and chance. From the fiery birth in supernovas to the quiet freeze of distant worlds, from planets that melt like candles to those that glow like stars, the cosmos writes an unending poem of transformation. Every world is a chapter in that story, born from dust and death, surviving against odds, and shining, however faintly, in the dark ocean of space. One storm may stretch across the entire circumference of a planet, with winds traveling thousands of kilometers in a single cycle, creating a relentless rhythm that defines its atmosphere. These storms, vast and untamed, can last for centuries, sustained either by the planet's own internal heat or by the unending stream of energy from its star. Lightning may crackle through clouds hundreds of kilometers deep, illuminating the endless layers like a slow, pulsing fire that never ceases. Jet streams and high-altitude vortices twist around the poles in mesmerizing patterns, carrying energy, gases, and dust in organized yet ever-changing flows. On these worlds, the concept of a calm day might not exist. The sky is always alive, breathing and shifting, wrapping the planet in perpetual motion. Such storms and systems reveal the true power and complexity of atmospheric dynamics, not only on the gas giants of our own solar system but also on terrestrial planets larger, denser, or hotter than Earth. They demonstrate that weather, in its grandest form, is an expression of the deep physical forces shaping every world in the cosmos. Some solar systems even include rogue planets, worlds that once belonged to a particular star but were flung out into the darkness between the stars. These wandering bodies drift for millions or billions of years through interstellar space, frozen and silent, until the gravitational pull of another star gently captures them. If the encounter is mild enough, the rogue planet may be drawn into a new orbit, joining a completely new solar family. These adopted planets often retain the chemical fingerprints of their original homes, unique atmospheric compositions or crustal elements that set them apart from their new planetary siblings. Their orbits, too, tell stories of disruption, often stretched or tilted, revealing histories of violent ejection or cosmic rescue. Over time, they may settle into stable configurations or drift again into the void, testaments to a universe that recycles and trades entire worlds across unimaginable distances. Some planets orbit stars too faint to be seen with the naked eye. There exist stars so small, cool, and dim that they emit almost no visible light. Brown dwarfs or tiny red dwarfs that glow primarily in the infrared spectrum, invisible without specialized instruments. Yet even these faint stars possess enough gravity to gather swirling disks of gas and dust where planets can form. The worlds that orbit them experience perpetual twilight, their skies dim, and their warmth faint. Some may be entirely ice-locked, while others, with thick insulating atmospheres, might trap enough heat to keep water liquid on their surfaces. These systems are fascinating because their stars burn extremely slowly, living trillions of years, far longer than our Sun, granting their planets vast stretches of time to evolve and stabilize. They prove that starlight need not be bright to create planets, and that life-bearing worlds might exist even under the faintest of suns. In some systems, immense clouds of comets encircle the star at enormous distances, forming vast halos of icy debris that stretch for light years. These reservoirs, remnants of the violent early days of planet formation, contain trillions of frozen fragments left over from when planets first coalesced from dust and gas. Occasionally, the delicate gravitational balance of such a system is disturbed, perhaps by a passing star or internal resonance, sending one of these icy travelers inward toward the planets. These comets may deliver vital materials like water and organic compounds, seeding young worlds with the ingredients for oceans and life. Yet they can also bring devastation when their impact releases colossal energy. These distant, invisible clouds mark the true outer limits of a solar system, tracing the boundary between a star's influence and the interstellar void. They are frozen memories of creation, preserved in deep space until gravity calls them home again. Not all planets follow the typical equatorial paths around their stars. While most orbit along the same general plane in which their star's disk once spun, some defy this order entirely. Astronomers have discovered planets whose orbits are so steeply tilted that they pass over the poles of their stars instead of around their equators. These polar orbits are extraordinary. Imagine a planet circling its star like a spinning top, moving up and down rather than around a table. Such bizarre alignments likely result from ancient gravitational chaos, perhaps a near collision with another massive planet, or the distant tug of a passing star that twisted the orbit into a near vertical orientation. These polar worlds experience extreme and unpredictable seasons as the angle of sunlight swings dramatically throughout their years. Their very existence forces scientists to reconsider how planetary systems form and stabilize, showing that cosmic order is not universal. Gravity can sculpt worlds into almost any configuration imaginable. Some stars, on the other hand, never manage to form planets at all. Though most stars are born surrounded by swirling disks of gas and dust, the birthplace of planets, not every disk survives long enough to give rise to worlds. Powerful stellar winds can blow the material away, or the star's radiation may heat and evaporate the gas before it can condense into solid bodies. In other cases, the disk simply lacks the right mix of elements, too little metal or rock to seed the growth of planets. Some stars are born in crowded stellar nurseries where nearby stars disrupt the fragile disks with their gravitational fields, leaving barren systems behind. These lonely stars shine quietly, encircled by nothing more than thin veils of dust, reminders that creation is never guaranteed and that even in a universe rich with planets, some stars remain forever childless. Meanwhile, certain planetary systems form under very different conditions. Most protoplanetary disks are rich in gas, mainly hydrogen and helium, with only a small fraction of dust. This balance usually produces gas giants and rocky worlds like those in our solar system. Yet astronomers have found some systems where the reverse is true, disks dominated by dust with very little gas. Such systems often arise from violent events, massive collisions between planetesimals, or the breakup of older worlds. In these places, planets that do form tend to be dense, rocky, and metallic, with little or no atmosphere. The absence of gas accelerates their formation, allowing solid material to clump together rapidly. However, without gaseous envelopes, these planets are exposed, unshielded from solar radiation or cosmic rays. These dust-heavy systems illustrate how planetary formation is not a one-size-fits-all process. Each system starts with a different cosmic recipe, yielding worlds as varied as the ingredients that created them. In other systems, planets orbit astonishingly far from their stars, so far, in fact, that their gravitational connection seems barely strong enough to hold. These wide-orbit planets can be thousands of times farther from their stars than Earth is from the Sun, taking millions of years to complete a single orbit. At such distances, the pull of the star becomes feeble, and even slight disturbances from passing stars, drifting gas clouds, or the collective gravitational tug of the galaxy itself can nudge these planets off course. Some of these far-flung worlds may have migrated outward over eons, while others could have been captured from interstellar space. They occupy the gray zone between being part of a system and being solitary wanderers. Their existence forces astronomers to ask, where does a solar system truly end? These distant planets stretch the definition of belonging, showing that gravity's reach fades gradually, not abruptly. Among the thousands of exoplanets discovered, a few have puzzled scientists so deeply that they seem almost artificial. These mysterious worlds exhibit patterns and properties unlike anything expected from natural planetary formation. Some are nearly perfect spheres, far more symmetrical than the chaotic processes of accretion should allow. Others dim their star's light in unusual, regular intervals, as if vast panels or geometric structures were orbiting rather than solid planets. The possibility, though speculative, that some of these objects could be artificial, perhaps massive constructs built by advanced civilizations, sparks both wonder and debate. While there is no definitive evidence of such engineering, These anomalies remind us that the universe remains filled with mysteries beyond current understanding. Together, these discoveries paint a portrait of a cosmos that is alive with diversity and motion. Planets can form, drift, collide, or vanish. Stars can nurture them for trillions of years or strip them bare in infancy. Systems can be orderly and flat, or chaotic and tilted, or barren and empty. Every world, from the frozen rogue to the fiery gas giant, tells a story of chance, gravity, and time. Across the boundless expanse of space, creation repeats itself in endless variations, sculpting beauty and chaos alike into orbits of possibility, reminding us that even amid the cold silence of the universe, there is constant, magnificent change. While natural explanations exist for unusual planetary phenomena, including shattered moons, dense swarms of debris, or complex cloud layers, the possibility remains that some of these objects could be megastructures or artificial habitats, sparking curiosity and the development of detection methods aimed at identifying deliberate engineering, such as unnatural chemical ratios, geometric shadows, or unusually stable orbits that defy gravity without propulsion. Although no artificial planets have been confirmed, the search itself underscores humanity's growing curiosity about the universe and the potential for wonders created by intelligences far older than our own. Some solar systems are so compact that their stars lie too close together for planets to survive. Binary and multiple star systems are common throughout the galaxy, yet not all allow planets a stable orbit. In these hostile arrangements, stars may be so close or their distances fluctuate so rapidly that no safe zone exists for a planet to form or persist, and any object caught between the stars may be torn apart by tidal forces, pulled into one star or the other, or ejected into interstellar space at tremendous speed. Even if a planet forms at a marginally safe distance, the combined light and heat from two stars may fluctuate wildly, creating extreme temperature variations that prevent the development of stable geology or atmosphere. These systems illustrate the limits of planetary formation and emphasize that the universe does not guarantee survival. Sometimes, the celestial dance is so violent that nothing else can endure. Other planets are slowly evaporating under the relentless heat of their stars or due to fragile compositions. These evaporating planets lose material as their surfaces vaporize and their atmospheres expand into trails of gas stretching like wisps behind them. Some may lose thousands of tons of mass every second, gradually shrinking until only dense cores remain, stripped of the layers that once defined them. Observations of subtle size reductions and chemical traces near stars confirm that even a planet in a stable orbit is not immune to decay. Stability over billions of years does not guarantee permanence, and entire worlds can fade, grain by grain, into the void. Newly formed planets, on the other hand, may remain molten for millions of years after birth, with residual heat from formation, ongoing collisions, and radioactive decay keeping surfaces in constant flux. These young worlds glow faintly in infrared light like embers in darkness, their thick atmospheres filled with steam, rock vapor, and sulfur gases, sometimes forming clouds of molten metal or glass. Beneath these searing skies, the planet may still accrete mass from smaller bodies, absorbing energy and chemical diversity until cooling and stabilization eventually allow the formation of a crust, continents, and oceans. Such fiery, primordial worlds offer glimpses into the early history of Earth, when it was a molten sphere slowly solidifying beneath a black sky, awaiting the first stone to cool. Some star systems display near-perfect symmetry, with planets orbiting at precise distances that reflect harmonic ratios and moons aligning and repeating, clockwork-like patterns. Orbital periods may lock into rhythms maintained over billions of years, balancing gravitational pushes and pulls to minimize disruption. These elegant configurations preserve alignment even as stars age or nearby objects pass, demonstrating the quiet intelligence of physics as it weaves balance into the chaotic motion of matter across cosmic scales. The beauty here is mathematical as much as visual, a testament to the laws of motion creating harmony without conscious design. Other worlds challenge expectations in more exotic ways, such as planets with oceans of liquid carbon dioxide. On worlds with the right pressures and temperatures, CO2 can exist as a dense, flowing liquid, forming seas that stretch across hemispheres and shimmer with frozen fog at the interface between air and fluid. Beneath the surface, pressures and temperatures rise, dissolving unusual chemicals and creating conditions in which life, if it exists, would be utterly alien. Volcanoes may erupt geysers of liquefied CO2, waves may carry mineral ice instead of water, and freezing rains may fall from dense, fog-laden skies. These worlds remind us that oceans do not always imply water, and habitability does not always require sunlight or blue seas, illustrating the universe's capacity to shape its worlds in ways unimaginable from an Earth-centric perspective. Some planets orbit so slowly that their years extend over 1 million Earth years. Their vast orbits place them at distances where starlight is faint, sometimes barely visible, and their warmth derives almost entirely from internal heat remaining from formation. Composed largely of ice and rock, these distant giants endure millennia of subtle gravitational nudges from neighboring stars or the galactic tide, gradually reshaping their orbits into long, slow arcs. Such worlds challenge terrestrial conceptions of time, with planetary cycles so vast that continents could rise and fall, atmospheres thicken or vanish, and entire hypothetical civilizations could emerge and vanish within a single orbit. Other planets are so massive that they defy composition from ordinary rock or even iron-rich cores. These superdense planets likely contain exotic materials compressed into forms unknown on Earth, some resembling degenerate matter similar to the cores of dead stars or remnants of catastrophic collisions between giant worlds. Their gravity is immense, compressing atmospheres to the surface and creating oceans of superheated gas or metallic rain, while pressures at their centers may fuse atoms into unusual lattices or new phases of matter. These extreme worlds illustrate that there is no single recipe for planet formation. Density, gravity, and time can produce forms that challenge familiar categories. Planets can also emerge from the remnants of colliding moons. Catastrophic impacts between large moons can eject clouds of molten rock and debris, which coalesce over time into entirely new planets. As the material cools, it forms layers and develops unique compositions, distinct from surrounding worlds, sometimes lacking elements typical of parent stars or containing unusual blends of silicates and metals. The orbits of such collision-born planets may be irregular or tilted, reflecting the chaotic circumstances of their birth. This process demonstrates the universe's capacity for recycling, showing that destruction can give rise to new creation, with worlds forged from the shattered remains of others. Other extreme planetary scenarios abound. Planets may form around stars so close to each other that tidal forces prevent stability, or stars may emit fluctuating heat and light that make atmospheres impossible to sustain. Young planets remain molten long after formation, their surfaces reshaped by collisions and heat, while mature planets may gradually evaporate under the relentless radiation of their stars. Oceans may consist not of water but of exotic liquids such as carbon dioxide, and years can extend millions of Earth years. Some planets are so dense that ordinary rock cannot account for their mass, while others form entirely from debris created in cosmic collisions. Some systems are perfectly symmetrical, others chaotic, some hostile to planetary formation entirely. Some may host planets captured from interstellar space. They represent the second generation of planetary evolution, demonstrating that the cosmos recycles its matter in ways both violent and beautiful, where destruction often gives rise to creation, and as the universe rearranges its building blocks, solar systems can change shape over billions of years. Planets, stars, and debris are not fixed in place. They shift and evolve under the influence of gravity, stellar evolution, and external perturbations. As stars lose mass to radiation and stellar winds, their gravitational pull weakens, allowing planets to drift outward into colder, more stable orbits, while passing stars or molecular clouds can distort the outer boundaries of a system, nudging comets inward and scattering moons or asteroids into new regions. Interactions between planets within a system can slowly alter orbits over eons, shifting conditions so gradually that the planets themselves may not notice, revealing that stability is a temporary state and that solar systems breathe and evolve like stars. Among these worlds are the superpuffs, planets so low in density that if placed in a large enough ocean, they could theoretically float, with sizes comparable to Jupiter but only a fraction of its mass. Their atmospheres inflated by heat and low gravity into layers of fluffy gas extending thousands of kilometers from the core, allowing starlight to pass through and enabling the study of their chemical composition. Superpuffs may form near hot stars before contraction or migrate outward into cooler regions, defying expectations of planetary density and reminding us that not all planets are solid, weighty spheres. Some are delicate, balloon-like shapes drifting in the vastness of space. Other planets orbit so far from their stars that an entire human civilization could rise and fall before they complete a tenth of their orbit, with seasons lasting millennia and temperature changes so gradual that geological shifts outpace weather, giving a perception of nearly frozen time, where a year is not merely a cycle but an era. Some planets remain hidden behind their stars for much of their orbit, detectable only through subtle gravitational tugs, faint changes in starlight, or tiny distortions in the motion of other planets, highlighting the limitations imposed by geometry and light and reminding us that much of the cosmos is concealed, with entire worlds remaining unseen unless we learn to watch for their shadows. Certain planets are permanently shrouded in thick clouds or atmospheric haze, never glimpsing stars, constellations, or the sun, living under eternal fog or diffuse glow where day and night appear identical, and surface conditions, whether scalding clouds of sulfur or carbon-rich gases or frozen methane smogs, prevent any natural understanding of the universe beyond the atmosphere. In binary star systems, planets can form around both stars or just one, experiencing double sunrises or shifting stellar companions, while the interplay of gravity and radiation shapes unusual orbits, dense asteroid belts, or incomplete disks, expanding our understanding of planetary science beyond single-star norms. In crowded stellar clusters, stars can steal planets from one another, transferring them into new orbits or ejecting them as rogue planets, leaving chemical or atmospheric signatures of their former stars, revealing the competitive and dynamic nature of galactic evolution. In the coldest reaches of space, planets can form entirely from disks of ice, composed of frozen water, methane, and carbon dioxide, gradually coalescing into planetesimals and eventually solid ice worlds that may remain pristine for billions of years, some developing underground oceans if internal heat melts their lowest layers, showing that not all worlds begin with fire. Some emerge from silence and cold, sculpted entirely from frozen interstellar matter. Rare solar systems may even contain mini black holes, remnants of ancient stellar explosions or collapsed cores, whose gravity subtly shapes the movement of planets and debris, clearing gaps in disks, creating strange orbits, or emitting faint X-ray signals, challenging conventional models of solar system formation and demonstrating the coexistence of life-bearing stars with remnants of dead giants. Across all these scenarios, solar systems are dynamic, evolving, and unpredictable, where destruction and creation intertwine, where planets drift, evaporate, hide, or form under conditions alien to Earth, and where time, distance, and gravity produce worlds that are molten, frozen, puffy, slow-moving, or marked by exotic chemistry, each system revealing the vast creativity of the universe, the impermanence of planetary stability, and the endless potential for discovery in the cosmos. These environments show that solar systems are not always isolated stories. They may inherit the shadows of the past and evolve around them, and among the most extreme examples are planets that exist solely as molten lava, located so close to their stars or formed so violently that their entire surfaces remain oceans of molten rock, reaching temperatures high enough to vaporize metals or turn stone into glowing rivers. Often with no atmosphere, as gases cannot condense or remain bound in such intense heat, leaving exposed material to melt and flow continuously as tides of lava rise and fall under gravity, their surfaces flickering in infrared light like coals in a furnace, sometimes cooling only if they drift farther from their stars, but many locked in permanent fire, reminding us that the universe does not guarantee stability and that some worlds are simply made to burn in silence for eternity. Other solar systems may form entirely without water. While water is abundant in our solar system, it is not guaranteed elsewhere, as some stars emerge in dry regions of interstellar space where hydrogen is plentiful but oxygen-rich materials are scarce, producing planets composed mainly of dust, metal, carbon, or silicates with almost no ice, leading to worlds with no oceans, clouds, rivers, or atmospheres shaped by evaporation, covered instead in sand, jagged rock, or volcanic fields, where life, if it exists, must rely on solvents other than water or chemical reactions driven by heat and minerals, illustrating that Earth's moist conditions are not universal, and many worlds may never experience rain, storms, or water-carved canyons, their landscapes sculpted instead by fire and dust. Some planets form at the edge of interstellar space, far from warm, bright stars, in the vast cold regions of molecular clouds where starlight is faint and gravity barely binds the gas and dust, allowing particles to collide slowly over millions of years to form small, icy, slow-moving planets orbiting stars so distant that light and warmth take centuries to reach them, with skies dark even at midday. Yet with pockets of warmth beneath frozen crust due to internal radioactivity, or accumulated pressure, showing that planets do not only form in the glow of suns but also in patient, quiet shadows. Some solar systems have sunless inner regions, where thick rings of dust or gas block light from reaching innermost planets, creating permanent twilight warmed only by indirect radiation or residual heat from formation, with skies appearing dim and foggy, devoid of stars, shadows, or sunlight, until dust eventually drifts outward or burns away, revealing sudden bursts of illumination that drastically alter surface conditions, demonstrating that light is not guaranteed even with a central star. Planets can be shaped like footballs, elongated under intense tidal forces from nearby stars or massive neighbors, creating cosmic ovals with bulging equators and compressed poles, causing surface strain, volcanic activity, shifting crusts, or deep ocean tides, while their atmospheres thin or thicken unevenly, generating extreme, rapidly changing weather, with these worlds potentially returning to spherical forms if freed from tidal forces or shattering into debris, showing that even fundamental planetary rules can be bent by pressure. Solar systems can form around stars so massive they burn through their fuel in mere millions of years, giving birth to planets despite the brief lifespan of their stars, only to face eventual destruction when the star collapses into a supernova. Yet in their fleeting existence they may host giant planets, molten moons, and rings of glowing dust stirred by radiation, seeding the galaxy with heavy elements upon stellar death. Reminding us that not all cosmic stories are long, some flashing briefly but leaving lasting impact. Some solar systems are so young that they still glow from the heat of formation. Dust, gas, and newborn planets radiate infrared light from collisions and compression, with even the planets themselves glowing, lighting skies before cooling into darker worlds, offering glimpses of our own solar system's early stages before oceans condensed and crusts formed, revealing the cradle of creation where chemical reactions raced ahead and surfaces remained molten or unstable. By studying hundreds of planetary systems, scientists are discovering just how unusual Earth might be. Many systems lack rocky planets or contain only giants of hydrogen and helium, orbit multiple stars, face intense radiation, or lack essential elements such as water or carbon, with some too young for life and others so old that habitable worlds may have vanished. Placing Earth in a narrow zone of balance with the right star, orbit, composition, and timing for life to develop and endure. Showing that our planet is rare, precious, and precarious. Through these studies, we see solar systems as dynamic, evolving environments, where worlds form, dissolve, collide, and begin again. Some planets orbit in permanent fire, some never touch water, some remain frozen in distant shadows, some are hidden behind stars, some are stretched or distorted, and some live brief, violent lives around massive stars, yet each system tells a story, each orbit turns time gently. And each planet embodies the vast creativity of the cosmos, offering glimpses of molten rivers, icy deserts, football-shaped worlds, superpuffs that could float, sunless regions, binary star dynamics, stolen planets, icy edge worlds, and systems glowing with formation heat. The universe recycles its matter through destruction and creation, shapes planets through fire, ice, and gravity, scatters them through theft and capture, hides them behind clouds and stars, and sculpts them with extreme tidal forces, demonstrating the impermanence and fluidity of celestial arrangements and the infinite variety of worlds possible beyond Earth. These cosmic realities remind us that planets are not guaranteed to host life, that stability is temporary, that sunlight, water, and heat are not universal, and that time, distance, and gravity can produce worlds where a single orbit takes millennia or a star's life ends before planets can mature. The universe will keep turning without you for a while. 2:11:10 You have done enough for today. Close your eyes. 2:11:15 Rest, and dream of other skies. Good night.